In this lesson, I'm going to give a brief introduction to linear programming. Linear programming is one of the most important optimization techniques, and there's a lot of theory behind it. There are many books written about it, but for us in this course on approximation algorithms, we're just going to treat it as a black box. So that means we just need to know what a linear program is, and we need to know that it can be solved efficiently, but we don't need to know the algorithms behind it. We don't need to know the algorithms that actually solve a linear program. So, what is a linear program? Well, a linear program is a mathematical optimization problem where we're given a number of variables. In this example here, we just have two variables, x1 and x2. Usually you have many more variables, and we want to optimize some function over these variables. Okay, in this case, in this example, we want to minimize a function of these variables, and then we could see this function that we want to minimize as a cost function. Often also the term objective function is used, and sometimes instead of minimizing the objective function, maybe we want to maximize the objective function. Okay. Besides that we want to optimize this function, we actually also have to make sure that what we choose for the variables, so the values that we take, satisfy certain constraints. As you can see here in this example, we have 4 constraints. For a linear program, what is crucial in this formulation is that both the constraints and the function that we want to optimize are linear. No quadratic functions or anything like that. Okay? So in a linear program, the objective function and the constraints are linear. So here's some examples of things that are not allowed. So here, this would not be a good cost function because, as you see, there's a term that multiplies 2 of our variables. So it's no longer linear in the variables. Here's another example where you see, again, that we have something which is not a linear term. So for the cost function, this should be the case, but also for the constraints. So again, something like this is not allowed, and also something like this, which is a combination of 2 linear constraints with an OR between them. That's not allowed. What you can have for the constraints is a number of constraints that should all be satisfied, but you're not allowed to have this constraint or this constraint is satisfied. Okay, so that's linear programming, and a good way to think about it is to visualize it and to look at a geometric interpretation of linear programming. And again, let me do this for 2 variables because then I can draw nice pictures. So let's look at the following 2-dimensional linear program. So we want to find values for 2 variables, x1 and x2. So that means that the solutions we can represent as a point in 2-dimensional space. Right? We have to find an x1 value and we have to find an x2 value, and together they define a point in my 2-dimensional solution space. Now, let's look at the constraints that we have. For instance, if you look at the bottom constraint, x2 is at least 0, well, that simply means that all the valid solutions must lie above the line x2 equals 0. So they must lie in this half plane. And actually something like that is true for all of the constraints. So if you look at the second constraint, which is here, then, okay, I can draw the line 2x1 minus x2 equals 5. That's a line. And now the constraint said that this should be at most something. So that means that our points should lie on a certain side of this line. Okay, and we can do that for all the constraints. So every constraint will give us a half plane. So here you see the third constraint, the fourth constraint, and so on. Okay, so each constraint gives us a half plane, or if we would have more variables, like in for 3 dimensions, we get a 3-dimensional point, and then our half planes are half spaces, so we get some kind of polytope in possibly some high-dimensional space. And our solution, or a solution that satisfies all the constraints, must lie in the intersection of all these regions. So in this case, what you see is that the intersection is here, and this intersection is called the feasible region, because a point in this solution space is a valid solution, a feasible solution, if and only if it lies in this feasible region. Okay, so this represents, you could say, all the constraints. Now let's look at the objective function, or if we want to minimize, let's say the cost function. Well, what we can do for the cost function is, actually, since we have a linear constraint, it means that the cost function says that we want to go as far as possible in a certain direction. And as you can see here, what we wanted to minimize was minus x1 plus 4x2. Well, that means if we switch the signs, because we want to minimize, we get a vector 1 minus 4, and we want to go as far as possible in that direction. Okay? But of course, our solution should lie inside the feasible region. So in this case, this would be the optimal solution. Okay? This is the solution to our linear program. Okay, so if you have a linear program, then the solution can be of different types. So you could say the standard, or the most easy type, is if you have one unique solution. So that's what we saw before. So we have a feasible region, and there's one unique point in the feasible region that gives us the optimal value. But there are more possibilities. It could also be that there's no solution. So here you see 3 half-planes, and as you can see, the common intersection of all 3 is empty. It's not possible to find a point that satisfies all 3 constraints at the same time. So in this case, the linear programming algorithm should tell you, sorry, there's no solution. Okay. But there's some more options. It could also be that the solution is unbounded. What does it mean? Well, suppose the feasible region looks like this, and now our objective function tells us that we want to find, let's say, the highest point. Okay, so in this example, let's say we want to maximize x2. Well, as you can see, you can make x2 bigger and bigger and still stay within the feasible region. So in this case, there is a solution. Actually, there are infinitely many solutions, of course, but there's no solution that gives us the optimal value, because you can always improve a little bit. In this case, what the linear programming algorithm should do, it should tell you that, okay, the solution is unbounded, and maybe along this particular line, you can continue all the way to infinity and keep on improving your solution. Okay. So there's one more type of solutions that you can have, and that's where the solution is bounded. Okay, so you cannot go all the way to infinity and keep on improving the solution. It's bounded, but it's not unique. So that's what you see in this example where, well, if I want to find, let's say, the lowest point, so my objective function will be to minimize x2, but I have a constraint which is horizontal. Then all points on the boundary of this constraint would have the same value for the objective function. And in this case, usually it's sufficient if your linear programming algorithm just gives you one of the points that optimizes your objective function. Okay, so let's summarize. So here you see linear programming in a slightly more general form. Okay, so now instead of having 2 variables, let's say we have n variables. Typically, in applications of linear programming, the number of variables is large. So I have n variables, let's call them x1 to xn, and I want to find an optimal value for these variables, so something that optimizes the objective function. So the whole linear program is specified by, well, you have to know the number of variables, but then you have all these constants that define the objective function and the constraints. Okay, so these CIs and also the AIJs are simply constants that are part of the input. Okay, and then given these CIs, the AIJs, and the BIs, then we want to maximize or minimize some linear function, okay, a linear function of these variables such that a set of constraints is satisfied. And like I said, in practice, typically what happens is that the number of variables is very large and also the number of constraints is very large. Okay, well, what I did here for the constraints, I wrote some linear function is at most some constant. You could also write some linear function is at least some constant. Okay, of course, you can easily convert one to the other by just switching signs. And you could also write some linear function is equal to some constant. And again, if you would just allow at most, then equality you can represent by two different constraints that together determine that it's equality. Okay, well, the previous linear program we could also write in a somewhat more concise notation by saying, well, we have a number of vectors. So the input is a vector C, the cost vector, a matrix A, and a vector B. And this matrix A and the vector B together determine the constraints. And now a linear programming algorithm should read this vector C, the matrix A, the vector B, and then compute values for the vector X, for your variables, such that, well, the objective function is optimized and all the constraints are met. Okay, and of course, as we saw, it can also happen that the program actually has to report that it's not possible, that the linear program is infeasible, or maybe that it's unbounded. So what is important for us is not how these linear programs are solved, but that they can be solved efficiently. So the only thing we need to know is this particular theorem saying if you have a linear program, then you can solve it in polynomial time. Where there's a lot of details, for instance, that here the input size is measured in terms of the number of bits. But again, for us, the only thing that we need to know is that, okay, if we can represent something as a linear program, then we're in business because we can solve it efficiently. The next lesson, we're going to see how to use this to actually develop approximation algorithms.